Welcome to my classroom. In this video, I will talk about how to work with matrices to handle an interesting task that requires the understanding of geometric interpretation of matrices and computer programming. The task is to draw a fern. Here is a fern. This fern is called the Barnsley Fern. It is an example of fractal. If you take a closer look and observe the pattern, you may notice that the figure is self-similar to arbitrarily small scales. That is, the figure contains a structure that the replication is exactly the same at every scale. It is a feature of fractal. Thus, when the repeated unit is identified, by using iterations, the figure can be drawn by computer in a fast and beautiful way. This Barnsley Fern was done with 1,000,000 iterations, and each iteration involves 3 transformations only. Wow, what are the transformations? How does it work? That is what I'm going to share in the video. I talked about a number of transformations in my previous video, matrix transformations in R2. Since 3 of the transformations will be used for the task, let me give a brief revision here before the start of the work on the task. Translation maps a point in R2 which is denoted by a 2x1 matrix xy to another point by doing addition. In the diagram, the unit square ABCD is translated by moving the origin to the point 3, 2. The image under the translation is still a unit square in the position shown by A', B', C', D' in the diagram. Scaling is a linear transformation, which is represented by a diagonal matrix alpha 0, 0, beta. The points on the x-axis are scaled by the factor alpha, and the points on the y-axis are scaled by the factor beta. For a general point xy in R2, the image of the point is given by alpha x beta y, which can be obtained by doing multiplication. In the diagram, the unit square is scaled by 3 along the x-axis and by 2 along the y-axis. The image becomes a rectangle as shown. Rotation is also a linear transformation, which is given by a square matrix. A standard rotation turns a unit square to a unit square shown in the diagram. A general rotation is given as, here the point on the x-axis is rotated by the angle theta, and the point on the y-axis is rotated by the angle phi. Note that the direction of the rotation is anti-clockwise if the angle is positive, and clockwise if the angle is negative. When the angles theta and phi are equal, the general rotation is a standard rotation. When the two angles are not equal, the rotation maps a square to a parallelogram. Suppose the composite transformation T combines 3 transformations in the way that it takes a scaling first, then a general rotation, and followed by a translation. Then the image of the composite transformations is given by, that is, let me use a concrete example for demonstration. Suppose a rectangle is given with a vertex located at the origin, and the dimensions are 1/2 as shown in figure 1. Assume the scaling factors are 1.2 and 0.8, and the rotation angles are 30 degrees and 45 degrees respectively, and the translation moves the origin to the point 0, 1. Then the transformation is given by the following expression. To find the image of the rectangle, we may check the images of the 4 vertices. That is, connect the points to form the image of the rectangle, which is a parallelogram as shown in figure 2. Now, we can start the work of the task by considering the composite transformation for building the fern. The structure of the building block contains 4 parts, and each part is done by the same composite transformations involving scaling, rotation, and translation, with different values of the parameters. The table shows the data of 4 composite transformations T1 to T4. To show the effect of these transformations under different values of the parameters, a rectangle is used. The rectangle on the left is the original figure with the height of 10 units. Apply transformation T1 to the rectangle. Because of the data chosen, there is no rotation nor translation, but the scaling which turns the rectangle into a short line segment with the length reduced to 0.16 of the height of the rectangle, that is 1.6. The image is shown as T1 in the figure on the right. Apply transformation T2 to the rectangle. The scaling factor is 0.85 in both directions, that the rectangle is slightly reduced. The angle of rotation is -2.5 degrees in both directions, that rotates the rectangle clockwise slightly. The translation 0.01.6 moves the reduced and rotated rectangle up by 1.6 units. Thus, figure T2 lies on top of figure T1. Apply transformation T3 to the rectangle. The scaling factors are 0.3 and 0.34 that reduce the rectangle almost to 1/3 of the original. The angle of rotation is 49 degrees in both directions, that rotates the rectangle anti-clockwise by 49 degrees. The translation 0.01.6 moves the reduced and rotate rectangle up by 1.6 units. Thus, figure T3 lies on the left and on the top of figure T1. Apply the transformation T4 to the rectangle. The scaling factors are 0.3 and 0.37 that reduce the rectangle almost to 1/3 of the original as well. Also, the new rectangle looks thinner as 0.3 is less than 0.37. The angles of rotation are 120 degrees and -50 degrees that flip the rectangle. Since the sums of these two angles is not supplementary, the image is a parallelogram instead of a rectangle. By the translation 0.44, the image is placed on the right side of figure T1 and lower than T3 as 0.44 is less than 1.6. How to use these transformations T1 to T4 to generate the Barnsley Fern through iterations? A very smart idea is to introduce a probability to each of these transformations. Here is a table of data with probabilities. Apply the formula of the composite transformation with the given data. We have the following table. This firm was created with 1 million iterations. You may pause the video, think and figure out how the probability helps for the drawing of the firm. It is good to write a program for the firm on your own. You may also study and learn from others' well-written programs in the internet. When you browse the internet and type Barnsley Fern in Python, an elegant program can be found in the website of Greeks for Greeks. This green fern was generated by this Python program. If you know Python, you may modify the codes by coloring the images of different transformations. In this picture, the images from T1 are green, images from T2 are orange, images from T3 are blue, and images from T4 are red. You may first think about why the images of these 4 transformations occur in this way. If you are still puzzled by the effect of the probability, you may number the points according to the order generated to see the pattern and the weight of the points generated by the iterations. Here is a sample of 50 points. The probability of T2 is 0.85, much higher than the other 3 transformations. Therefore, the orange points occur more often and in a continuous way that the orange points jump up by the transformation due to its component, the translation 0.01.6. When the points are given by other transformations, the next round of points coming from T2 form another column of orange points. You may pause the video and observe the numbers and the patterns to understand more about the effect of the probabilities related to these transformations. It is a good fun to change the probabilities as well as the values of the parameters and observe the effects. Then you will see the probabilities in the table are well chosen for the fern, drawn fast and nice. The task is composed of two parts. The first part is the mathematical idea behind the work. The points built up the fern are created by a simple composite transformation which involves scaling, rotation, translation, and matrix operations. I suppose it is easy to understand. The second part is about computer programming. I have used a program in Python for drawing. You may study the codes and understand the structure of the iterations and see how it works smartly. If you know other computer language like C++, you may write your own program for the fern and see if you can draw the fern by the other way round. This task is a part of a talk on fractal I attained many years ago. The beautiful picture and the simple idea impressed me. To prepare this video, I study and learn more from the codes in Python. When running the program, the Barnsley Fern is created on the screen of the computer in a wonderful way. It is an interesting experience to me. I hope you share the joy too.